Is a great pleasure being in Portugal again. As she mentioned, I was here in 2004. This time I have the privilege of having brought my wife along, so she can also enjoy a little bit of Lisbon, at least, while we are here. My talk today is going to perhaps go back into the past a little bit. About the vanilla theory. I know that some of you have worked. I hope my internet is still active. We will see just now. Some of you have done work in vanilla theory. Angel is here. He and I know each other, I think, since Quebec. I think we first met at EIEM in 1990 something. So I hope some of the things I will be talking about the vanilla theory will be new to some of you. I assume all of you are familiar with the vanilla theory, but I would like to highlight a few things from my perspective, which may be a little bit different from others. And perhaps just very quickly, I hope the internet is still active. If you want to find my web pages, I have two ones, which is my homepage for dynamic mathematics learning. That one there, which you can probably find by just Googling my name, or my dynamic geometry sketches. In fact, if you Google dynamic geometry sketches, it will come, if you just Google dynamic geometry sketches, it will come out probably at the top of a Google search or second from the top, which should take you to this site here, just to show that. This is the web page of my dynamic geometry sketches site, which includes a variety of, let me perhaps just see if I can convert this one sketch here. There we are. Java, unfortunately, some of these sketches I've not updated. All of them require the latest version of Java, and depending on your security settings, it might be problematic running. There are some sketches there that are all dynamic that can be used by students. And then I have a number of my papers listed down here, mostly on geometry, as you can see there, and there are also explorations for students. And if you want to go back to my downloadable articles, there is a link at the top there which will take you to my web page, which includes a number of my papers listed under mathematics education. As you can see there, I think the one that we spoke about earlier today about EIEM, Dom Pedro, is an example of the explanatory and discovery functions of proof, is my EIEM 12 paper there. And then I have a number of papers at the bottom which are more mathematically inclined, although I always try and include, even in my mathematical papers, I try and include some educational aspects, although some are probably much more mathematical, like this one, which is more pure mathematics than geometry education. Okay, I will come back maybe later to some of that. Perhaps just to mention also that the talk I'm giving is not an entirely new talk. I have given this talk in, well, I should change a little bit for today, but I have given this talk in Brazil as well as in Croatia on the vanilla theory. There is also a video that was recorded of my talk which is available online. It is also listed on my webpage there. There is a link there. That should be easy to find. Anyway, let us get started. We only have an hour and 15 minutes for both presentation and some questions. I think the question which prompted the Van Hille's, Pierre Van Hiele and his wife to investigate is a familiar problem to most of us around the world. Why do children who are successful in algebra or in other parts of mathematics, why do they struggle with geometry? There seems to be this discrepancy, and I don't think things have changed all that much, despite many years now of research into the problem. It is still something that is problematic. There I just referenced the doctoral dissertations of the Van Hille's in 1958, which was done under the supervision of the famous Freudenthal. Just to summarize, I think you're all familiar with this. Basically, they came to the conclusion that the difficulty that children have with geometry is that it is presented at a higher thought level, a higher level of thinking than that which the pupils have. And of course, then they characterize the levels, and I'm just going to focus on the first three levels because I think they're the most important. I think all of you are familiar with these. There's a visual level where children recognize shapes by their experience. They can recognize different shapes, but they don't necessarily know the properties. Then there's the level of analysis where they start learning that shapes have different properties. They also learn, perhaps very important, they also, I think the language component comes into play here. At the second level, they need to know what certain meaning of certain terms are, quantifiers are, two and only two, things like that, as well as technical terminology like opposite and adjacent, etc., what that means. And then only at the third level, students are capable of logically starting to order the properties of figures by making short chains of deductions and understanding the class relationships between figures. For example, seeing squares as special rectangles and so on. Now, according to the Van Hiele theory, this is a strict hierarchy. Children first have to master level 1 before they can progress to level 2, and master level 2 before they can progress to level 3. Perhaps I like this diagram, which is based on a diagram, a characterization first by Fuse, Geddes, and Tischler, and others have modified it a little bit. I've used more or less the same kind of diagram. I think it helps to think about the change in perspective, how children's thinking changes. At level 1, they tend to focus on this figure, on the individual figure that they're working with. At level 2, the focus shifts to classes of figures, and only at level 3 do they start dealing with the definitions of those classes of figures. So the structure of thought here is mainly visualization, naming, their sorting, their classifying would be based on visual sorting. Here they would start recognizing properties as characteristics of whole classes of figures. And then, of course, at this level, they start noticing logical relationships, that the one property may be deduced logically from the other property. Examples of their thinking roughly could be something, if you ask children, if you give them activity to do, why have they sorted parallelograms? They would say, because they look the same. And they may say rectangles, squares, or rhombus are not parallelograms because they do not look like them. So their arguments would be from a visual perspective. However, at level 2, they would tend to start referring to properties that they have now learned. They would say a parallelogram has, if you ask them, explain what a parallelogram, they might start listing all the properties that they know about the parallelogram, and they might argue that a rectangle is not a parallelogram since a rectangle has 90-degree angles, but a parallelogram not. And of course, by the time they get to this level, they now start noticing that opposite angles imply opposite sides parallel, or if you have opposite sides parallel, that implies opposite sides equal. I'm now talking about quadrilaterals, obviously. And opposite angles equal imply opposite sides equal as well. So these are different possible definitions, and also things like if you have a quadrilateral with bisecting diagonals, that would imply half-turn symmetry, and so on. So one could start dealing with the issue of how to define, say, a parallelogram. That, in a rough, I think, gives us some idea of the first three levels. Perhaps something to mention that is not often mentioned, and I usually mention this to the postgraduate students that I've worked with in the past, that there's a tendency sometimes when people write materials, particularly learning materials at school level, to kind of think that visualization is where you start, and then you do analysis, and then you do ordering, and then you get maybe to the axiomatization and the formal higher levels of the vanilla theory. But, you know, once you get to these levels, there's no longer visualization, there is no longer analysis. And I think, to me, that is a somewhat incorrect interpretation of the vanilla theory. I think there is some need for visualization sometimes at these levels as well. So it's not something you finish it off and you write an exit exam and now you never have to do visualization ever again. The nature may change, but visualization, I think, is important at all levels. And I think certainly with diagnostic tests that we have designed, and I know other people have done a lot of research on vanilla theory, it seems to come in waves when people become interested in the vanilla theory again, then there's a lot of research, and then there's a few years that there's no research. But you will find that quite often some of the problems students have with higher level items intended for higher level, actually the problems lie with a lack of visualization. They cannot visualize, say, corresponding angles in a different orientation than the standard prototypical presentation that appears in textbooks, etc. So visualization, I think, is something that is important there. Just very quickly, I'm going right back to the 1960s. Versa reported Russian research that was done in the 1960s, where the Russians had a big national study to investigate the same problem we've mentioned, why are children underperforming in geometry, and they found the following discrepancy, that in the first 5 years pupils, learners were expected to become acquainted via level 1 activities with only about 12 or 16 geometrical objects and associated terminology. But then suddenly, by the time they get to grade 6, look at this, they now suddenly have to learn 100 new geometric objects and terminology at level 3 understanding of geometry. So there's suddenly a great leap. And I'm not sure in other countries, but certainly in South Africa, I think there is also very much this kind of gap, that very little geometry is done in most of the primary school, and then suddenly by the time they hit junior secondary or maybe late primary school, suddenly they are thrown into the deep water with geometry. I think that's the first problem encountered there. Of course, the Russians called grades 1 to 5 as a prolonged period of geometric inactivity, where they don't do any geometry of much significance beyond maybe just learning a few names and a little bit of terminology here and there. I think in the paper that I have written for the proceedings, I have a few more references, but one of the studies I did with one of my students, Rafael Niusani, he's since passed away, unfortunately, found that about 45% of pupils investigated in grade 12, the exit level in KwaZulu, in those days, today is called KwaZulu-Natal, had only mastered level 2 or lower of the vanilla theory, whereas the examination, the exit, assumed mastery at least at level 3 and beyond. In those days, we had a high standard, I think, of geometry questioning, and it certainly flags a serious problem there. Just a few other studies very quickly. Wu and Ma, for example, investigated in 2006 that almost 30% of grade 6 learners in Taiwan were already at Van Hiele level 3, whereas in South Africa in grade 11 we had 28% in 1987, and a more recent study in 2005 showed that there were 18% in grade 7 in South Africa who were at Van Hiele level 2. A big discrepancy. And I think the discrepancy is explained in terms of the curriculum. Because in Taiwan, they, as in many Asian countries, they do a lot more geometry from early ages. In Japan, for example, they start dealing with things like congruence in an informal way in the very first 3 grades already, with the conditions for, for congruency of triangles, side, 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 and so on. Simply by playing, asking learners how would they, with straws and so on, construct triangles, and figuring out different conditions, congruency conditions, in an informal way. So I think in most countries, and I'm not sure exactly what the situation is here in Portugal, how much geometry is done in the primary school, but I think compared to Asian countries, I think we don't do a lot. One of the things that Dina van Hiele in particular in her doctoral dissertation focused on was the use of tessellations, and her doctoral dissertation is perhaps not all that well known. There is an English translation. I'm fortunate because I speak Afrikaans, which is very similar to Dutch, that I could read the original, but there is an English translation of her thesis that was done in a project by David Fuse, Dorothy Geddes, and Tischler in the New York. They were from New York. They published that, I think, through NCTM as part of that project. There is an English translation. And I suggest that people that might be interested here in following that up have a look at her work, because I think it is often neglected, the way in which she envisaged how we should approach it. For example, some of the activities that she would recommend doing and that they found useful in their design of activities was that children should engage, and I'm going to show here how we would perhaps now with the technology we have now that they didn't have at the time in 1958, how we might engage in creating a tessellation quite easily. And I'm not saying this should replace any hand construction, which by hand construction and actually physically manipulating tiles, but I think this is something that can complement that. Let me just mark a vector there. And now we can very easily tessellate that, because we now have a parallelogram, and as we know it has opposite sides equal, so I can very quickly create a tessellation there, and then I can create define a vector in that direction. I'm using Sketchpad here. I assume all of you are familiar with GeoGebra, which most people use. You can do the same thing in GeoGebra. I'm just using this because it's convenient for me. And I can translate down, etc. And the idea is not only to create a nice pattern like this that kids enjoy in the primary school, but to now start identifying parallel lines, and the advantage of using tessellations is you have parallel lines in this direction, you have parallel lines in that direction, and of course if it's dynamic you can also move it around, so it helps children develop a much better visual intelligence than, I think, just working with a static school textbook where everything is fixed, nothing moves, and they see only in the standard configuration. Parallel lines are normally drawn horizontal, as we know in the textbooks. So having some facility in this, I think, is useful. And then having them identify things like ladders and saws. Here, for example, is a saw. By that they mean the zigzag, where this angle is equal to that angle, what we normally call alternate angles, or we now have this angle here equal to that angle because we have a ladder which is lying on its side, the idea of corresponding angles. But you also have, for example, this angle here is equal to that angle. These are the sort of activities that Dina van Hiele felt was very important for the groundwork to prepare learners for high school geometry. I'm not sure how much of this is really done. And I think one can do it both practically but also with these sort of dynamic tools that we have available today. Of course, if we now go to Van Hiele level 2, well, perhaps this is also still Van Hiele level 1, towards 2, where here we have a zigzag. That angle is equal to that one. They can identify that as a zigzag, and this one is equal there to that one because we have a ladder, and we can see in that configuration that those angles lie on a straight line. Of course, if it's dynamic, it is far more convincing than just having one specific case, and I think that's the advantage. We can also see it in different orientations. This angle is equal to that one. Have kids identify things like that. And there again we have the three angles. E and C and D are forming a straight line, but in a different orientation. We can also see things like this triangle is congruent to that one. We know they are tiles. So this one here, the base here is half of that. And is also parallel to that. So there we have the midpoint triangle theorem illustrated there. There are various other things. For example, here we have the sum of these two angles are equal to those two angles because this angle is equal to that one and this one is equal to that. Have them identify that on a visual level. So Dina van Hiele developed many of these sort of activities which I think illustrate how we can use tessellations more productively. For example, level 1 might be on a tessellation like that to identify parallelograms in different orientations and of different shapes. That would be level 1, just visualization. Level 2 would be more focusing on properties. Here we have a zigzag. This angle is equal to that one, because we have a zigzag or saw, and this one is equal to that one because we have corresponding angles equal, so therefore we have opposite angles equal. So making that discovery inductively, but notice also it's not only inductively, but it is also just about a proof, a general proof. But the idea is that the activities at the previous level should support higher level thinking and not based beyond measurement. I think it's important that the Van Hieles often emphasize that geometry is not about measuring angles or measuring distances, but it is about the relationships between those. So they would oppose measuring this angle and measuring that angle to show that the opposite angles are equal. They feel that that does not prepare learners for a proof. You should do activities that would prepare them for the type of thinking that is necessary for proof. And for example, here the proof is formalized. The exploration there, where we say at level 3, angle 1 is equal to angle 2 because we have a saw. Angle 1 is equal to angle 3, that's a ladder, using the terminology that she would encourage, and that gives us angle 2 is equal to angle 3. That sort of activity. Perhaps I want to emphasize here the idea of conceptual structuring. which I have referred to earlier, is that lower level activities should provide the appropriate conceptual substructure for the next level. And they emphasize this a lot, but I think it's often in many work that I've seen, and certainly when people translate the Van Hiele's work into didactical materials, this aspect is often not, I think, given sufficient importance. As I said, they would not support an activity, for example, if we want learners to discover that the sum of the angles of the sum of the angles of a triangle add up to 180, just to measure the three angles and then add them up to show that they are always 180, because they would say, yeah, that shows that the sum of the angles is 180, but it provides no conceptual substructure for them to help them to get to the proof. And ultimately we want them to get to a proof. And I'm not even talking here about the function of proof, which perhaps I will just allude to a little bit later as well, which is not really part of my talk. What they would say, for example, well, as I said, measurement does not provide appropriate, in most cases, conceptual scaffold. For example, if we want learners to discover that the sum of the angles of a triangle from a tessellation or from a transformation activity like this, we can translate the triangle, have learners note that this angle has to be equal, this one here, has to be equal to that one. Why? Well, it's pretty obvious at the elementary level. We have just moved the one triangle there. We've translated it. So it doesn't matter the shape of this one, this angle will always equal that one. And then using the same argument for rotation, note where that angle is moving over here. So these two angles here, the one there and there, must be equal. Of course, we recognize our zigzag there. And it doesn't matter the shape. We can now see there that they lie on a straight line. And the beauty, of course, if we use dynamic geometry, is we can change that to see it doesn't matter. Now, they would argue, notice we're not using any measurement, we are just using an experimental demonstration. This is, of course, not a proof, but we all can see the proof there already, because you actually have the zigzag, the alternate angles. We also have the ladder there. And I think an activity like this is much better than just measuring the angles with GeoGebra or whatever program one is using, just adding them up. Because this one is preparing the groundwork for the proof. And perhaps on that note, as many of you probably know or may know, is that much of my work has been on proof and about the function of proof. I think when we use dynamic technology like this, which is quite convincing, even much more so than experimental work where children do construction and measurement themselves with paper and pencil, this is definitely more convincing. They tend to trust what the computer does and what they see on the computer screen. I think the emphasis that I've tried to promote in terms of the role of proof is that we should focus not on verifying that things are true, but we should challenge learners to explain why things are true. And that proof then tries to answer that aspect of why we are trying to prove things. We are trying to explain why they are true in terms of other results. In other words, it's a bigger focus on the explanatory function of proof. Perhaps about defining very quickly, the Socratic didactician Hans Freudenthal writes, would refuse to introduce the geometrical objects by definitions. But whenever the didactic inversion prevails, deductivity starts with definitions. In math research, most definitions are not preconceived, but the finishing touch of the organizing activity. The child should not be deprived of this privilege. He made that statement already in his book 1973. However, if we look at much of math education textbooks, there's often, and I think a predominant obsession with introducing new concepts by means of a definition. You find textbooks in the primary school that start with a definition. They say, a rectangle is a quadrilateral with all angles equal. Now, if you are a young child, think back on the Van Hiele theory. In the Van Hiele theory, they will only understand that definition if they are already at level 3. But we give that to them as their first introduction to a rectangle. That is, I think, a sin. Well, somewhere I think Hans Freudenthal says something quite explicitly like that. It is a sin to a child's mind to introduce them to mathematics by formal means. There's many examples. A symmetry is an exact correspondence in position or form about a given point, line, or plane. We see these things. A prime number is a number only divisible by itself and by 1 excluding 1, and then some examples are given. This is the way in which textbooks are written. A function is a mathematical relation such as each element, etc., and then we give some examples. We start with a definition. This is the way in which the textbooks are written, and I think that is really problematic. I think we need to engage learners more in definitions. I would argue that children do not naturally learn what things are from just being given and learning their definitions. And I think research that has been done in the past 30, 40 years on the Van Hiele theory, I think have shown this. Children may be able to regurgitate the definition, but not really accept the definition, and not even be able to apply it in a consistent manner. They just don't learn that way. I think children learn, I think what is research in geometry and other areas of mathematics, often develop a sound understanding of many things without having or knowing their formal definitions. This is an example just of the concept of a chair. All of us know what a chair is. And, there are many different images that may be conjured up. And an activity that I would often give to my master's students, postgraduate students, would be for them to write down a formal definition for a chair. What is a chair? Or a table, for that matter. It's not that hard, but it does require them thinking a little bit. We all know what a chair is. But did we learn what a chair is? Did our parents tell us, blah-de-blah-de-blah, a chair is this or that, or that, or that, like in a formal definition? No, we learn by association. And I think we forget this when we get to mathematics, and particularly geometry. We learn from varied examples, by examples and, of course, counter-examples. There's been quite a number of research in that area as well. Here's an activity that I've used from my Rethinking Proof with Sketchpad book, which more or less is like this. A quadrilateral, like the following, is called an isosceles trapezium, trapezoid. In America, they would call it. And this would be to assist the transition from Van Hiele 1 to Van Hiele 2. And the idea here is, note I don't, at this stage, there's no point in giving a formal definition, and we want to engage learners later on in formally defining the figure. So there's no point in giving them what they need to do or what you would like them to do later on. So we just say, something that looks like this is a isosceles trapezium, and now they can explore what is that shape. Even, is that still an isosceles trapezium? Well, according to what we said there, that is still an isosceles trapezium. How is it still different or the same? I have a little bit of an argument about, does it still have the same properties in terms of sides? For example, this side is equal to that side, and I'm not going to measure it. And perhaps I want to say that I'm not totally against measurement myself, despite what I said earlier, and despite what the Van Hiele's say. I think there is a place maybe to have learners measure maybe the lengths of opposite sides, but perhaps also to explain in terms of the symmetry of the figure why that is so, that this is simply the reflection of that. Okay, that is why it doesn't matter how I drag these, those two will always have the same length because of the reflection. That's the way in which children constructed that figure. Sorry, I neglected maybe to mention that, by reflecting this line over there. What can we say about angles? This angle maps onto that angle under reflection, which we can dynamically illustrate. I'm not going to do that. This angle similarly maps onto that. Is this still the same there? Well, we still have a mapping here, but the issue is what happens to the angles here is a little bit more complicated. When we have a cross figure here, one can create a very nice Lacatosian type of experience for learners here, because the sum of the angles of that figure, if you just measure these angles, are no longer going to be 360 degrees. So it challenges what we mean, the meaning of angle, and how we want to define angle here. I'm not going to go into that right now, but that can create a nice Lacatosian type of scenario where even with practicing teachers, they are very baffled when I throw something like that. Usually what they do is they do monster barring. They say, no, that is definitely not a quadrilateral anymore. That's a first kind of reaction to something like that. Anyway, I don't want to spend too much time on that. But I just wanted to say, can you logically explain your conjectures in terms of symmetry? Notice the wording that I'm advocating that one should use that is more meaningful to learners. And certainly some of the research that I have done and some of my students is that learners tend to find it far better that we talk about the explanatory function of proof rather than trying to verify that it is true. They can see it is true. They are convinced by the empirical experience. And then perhaps dealing with some issues of hierarchical classification. Can an isosceles trapezium sometimes be a parallelogram? Well, yes, it can. There it is a parallelogram, a rectangle, but it can't be a general parallelogram. Notice my wording. I'm talking about a general parallelogram where some of the sides lie like this and others lie like this. It cannot be that, but it can be a rectangle, or it can be become, if I drag it sufficiently, I'm not sure if the screen there corresponds to my screen here, I can drag it roughly into the shape of a square as well. So a square is a special case here. Notice here I'm deviating somewhat from the Van Hiele theory, because the Van Hiele theory, strictly speaking, advocates that hierarchical classification, class inclusion occurs on Van Hiele level 3. I think we have sufficient anecdotal evidence and some hard evidence as well that using dynamic geometry like this, where children can drag and see that shapes can be changed into more special cases, assists hierarchical class inclusion far better than just a waving of hands and arguing from a formal definition point of view. And in fact, that brings me to hierarchical classification, class inclusion. I think research over the years, there are many, I think Angel's research and John Pegg, Berger and Shaughnessy, would find that young learners in particular would be predisposed towards visual or partition definitions, as I like to call them. For example, if you ask them to define a rectangle, they would say it is a figure which looks like this. They would draw one, or they might be able to identify it from a number, and they would focus on saying, well, this is a rectangle because it has two long and two short sides. Okay? which immediately, of course, excludes what I just showed on the previous case where we can get a square. In fact, some textbooks, I think, I've seen certainly in South Africa, that describe a rectangle as a stretched out square so that it has two long sides and two short sides. Now, the person who wrote that textbook thought they were probably very smart by starting from what is known more, the square, to now helping kids make sense of it, but in fact that's an inverse hierarchical and mathematically incorrect relationship. Basically, we do create in mathematics new objects by relaxing conditions, which essentially you are doing here. You're relaxing the condition that all sides have to be equal when you stretch it out like that, and we're just doing an affine transformation in a sense. But yeah, it creates problems in the primary school. I think many of our problems in geometry start in the primary school. I think we need to do more research in geometry in that respect. Anyway, I think in the primary school also traditionally learners are introduced to rectangles, etc., parallelograms as static geometric objects. They are maybe given cardboard cutouts or static images in paper on a textbook page that are not dynamic, that don't move. And we were just talking earlier today about primary math teachers who have sort of a phobia about computers and even calculators in the primary school. They don't want to engage in this technology because they didn't have it at school, and perhaps they're also afraid that the kids might be better than they are at the technology, which are quite often they are. So all they rely on is maybe a little bit of demonstration on an overhead projector of static images, and this compromises, I think, their geometric development, I think, later on. I think we need to, if we want to improve geometry, I feel, as Crane and Rubinstein already said in 1993, we need to think of ways of establishing an inclusive classification of quadrilaterals before engaging them in formally defining the quadrilaterals themselves. And let that sink in a little bit. This is before you are letting them engage in the definitions. In other words, they are referring, and in 1993, dynamic geometry barely existed. They were referring to using flexible mechanical models. And I remember designing things like that. We had flexible models of quadrilaterals and that could squeeze in so that I could show students and learners even at school. Now we have dynamic technology where we can do this, and I think this is an area where there has been some recent research. I know some of my Korean colleagues have done some research where they have shown, I think, some modest improvements. One mustn't expect, I think, with any kind of research that we are now going to suddenly have 100% improvement by the introduction of GeoGebra or anything. But if we have a modest improvement in learners' understanding, I think that is already a step forward. But I think this is something that we need to look at. Perhaps if the website is still active, we can go to that activity there, which I have a. Let me just copy that. If the website is still active, it should go there. That is linked, but it's just a little bit quicker. This is an activity that I designed, and I'm not saying this is how it should be done. Not at all. And it's just a suggestion. Classifying quadrilaterals visually by dragging. This is from a collection of activities that I have on my webpage. You will see a link there under the student investigations. It's just this one, grades 1 to 7. That possibly what we should do, and I think some research on this would be valuable. And certainly I think teachers more experienced in primary school could come up with something better. That a figure that looks like this is called a square. And having children either drag it or, well, both, I think animate the square so that it can move and it can change its orientation and position so that it can recognize a square in many different orientations, but well, unfortunately, the projection is not entirely similar to what I have on screen here. There, it sometimes looks like a rectangle there instead of a square. It should remain like a square all the time. It's a little bit misleading. I mean, that is one of the problems of having technology. So if you do this with learners, I suggest that you make sure and set it up. I mean, I can play around. I don't want to play with the settings so that it has a proper representation there. Otherwise, you are being counterproductive. But at least I'm not talking to children here. I'm talking to adults here. Of course, now when we do the same thing for a rectangle, whoops, there we go. We now see something different. I mean, here the shape is actually changing. In the previous one, the shape shouldn't have been changing, but here the shape changes, and sometimes the rectangle can be long and short, but sometimes it can be quite fat and thick, but sometimes it looks like the one before. It can become a square. And I think this is very important when you first introduce it to primary school learners. Otherwise, that partition thinking of thinking a square and a rectangle are always disjunct from each other. That becomes fossilized, and to change that later is really problematic. I think most Van Hiele research has shown that once kids have gotten stuck on these things are different. Perhaps I should mention some of the research I did for my own PhD. One of the students I had an interview with was a student in grade 11 that year. His father was a mathematician, and I asked him, how would you define a parallelogram? And he just gave me the textbook definition. A parallelogram is a quadrilateral with opposite sides, two pairs of opposite sides parallel. But I saw that in the way in which he rattled it off, that he wasn't quite happy, and I said, you know, are you happy with this definition? Do you like this definition? And he immediately, mathematically confident, he responded and said, no, I don't like that definition. And I immediately asked the student, well, how would you like to define a parallelogram? What would be your preferred definition? He immediately responded and saying, and this is a grade 11 student already, and he was a mathematics, South African mathematics Olympiad top 10 finisher. So we're talking about a very talented student mathematically. He immediately answered and said, well, I would define a parallelogram as a quadrilateral with opposite sides parallel, but not all sides equal, excluding rhombuses, and not all angles equal. So this was his mindset. And it was not a matter of mathematical incompetence or whatever. It was just that this idea that we should exclude squares and rectangles from parallelograms had become fossilized in his mind. Very talented student. And we should not forget, this was actually what Euclid did himself. Euclid actually excluded rectangles and rhombuses from the parallelograms. Are most of you aware with that? I mean, I can show you on the internet Euclid's translation. I mean, Euclid's Elements. Let's perhaps go there very quickly. Euclid's Elements. Euclid, in fact, did that. I think this one here should take us there. This is what's nice. Let's look at book 1. If we page down, you will see here, definition 22 of quadrilateral figures. A square is that which is both equilateral and right angled. An oblong, that which is right angled, and an oblong is a rectangle in Euclid, that which is right angled but not equilateral. Euclid excluded the squares. So the student was in good company. We've changed since then. The student was in good company. He was at the level of Euclid. A rhombus, that which is equilateral but not right angled. Notice excluding from the rhombuses the squares. And he says in a rhomboid, that which has opposite sides and angles equal. Now the rhomboid is what we call a parallelogram today, which has opposite sides and angles equal. Notice it is not an economical definition. In other words, it has more properties than is necessary. I call it an uneconomical definition, but is neither equilateral nor right angled. He's excluding the rhombuses and the squares from that. And then let quadrilaterals other than these called be trapezia. We give a different definition. But notice he was a good company, the student. So it is a matter of choice, and I think this is another. I wrote a paper once about the role of hierarchical, of a hierarchical classification of quadrilaterals, where I think it is important to convince learners also, apart from creating preparatory things with dynamic geometry, but to convince them of the value of classifying things hierarchically and to develop some activities in that regard. One of the things of my PhD, which I never wrote up and published, was we did a classroom experiment in grade 9 with learners where we, my supervisor and myself, I see my time is almost done. 5 minutes, okay. I started a little bit late, yeah, okay, 5 more minutes. Anyway, where we had a classroom experiment with grade 9, and both myself and my supervisor, we co-taught this particular course. And what we allowed the learners to do when we started engaging with quadrilaterals was allow them the option to choose partition definitions or to choose hierarchical definitions, class inclusion or exclusive definitions. Then insisted that they be consistent with their definitions that they had chosen. And initially some of the students were very rigorous. They insisted on their partition definitions, but they soon realized as we went on and when we had to start proving riders and stuff like that, that it became very clumsy and very cumbersome because it duplicates the number of proofs you have to do. It becomes problematic in the sense that you not only have one theorem to prove, but you now have 2 theorems to prove. You have to prove it works for squares, you have to prove it works for rhombuses, you have to prove it works for rectangles, and then for a parallelogram that looks like this. So you have 4 proofs instead of just 1 proof. So the hierarchical classification is there to simplify our mathematical deductive system. Because if you have this class inclusion system, then the theorem for the parallelogram immediately applies to the special cases below. But we need to design activities, I think, to convince learners of that. And I think that is something that at Euclid's time did not exist. Anyway, I think I need to move on a little bit. This is one of my pet topics. Okay, there is that activity. I'm going to skip that. I've just shown that. Now, how do we get to defining an associative trapezium? One of the activities that I usually would use with my postgraduate students, or practicing teachers as well, is having them do the activity, discovering and formulating. I find that teachers have difficulty formulating, just using quantifiers like at least 1 line of symmetry through a pair of opposite sides, because it can have 2 when I drag it into the special case. It has equal diagonals, etc., etc. It's also cyclic. And then to engage them in activity, to ask them, for example, now, can we choose necessary and sufficient conditions from those? to define it. Now we're dealing at the formal level. Now we're at the systematization level, level 3. And one could ask, how would you over the phone or via SMS explain what an isosceles trapezium is to someone not yet acquainted with it? Make it as short as possible. Test it by making maybe a construction by paper and pencil, but preferably, etc. Try formulating alternate descriptions. Can you prove it? Then perhaps giving them some activities like this. Suppose somebody said this would be a definition. A isosceles trapezium is any quadrilateral with equal diagonals. And usually often when I ask this of teachers, and they say, oh yeah, that's a correct definition, that will work. And of course then having them maybe work through an activity like this, constructing something that has equal diagonals, understanding why the construction works. Oh, they say, yeah, it's correct. They say, well, drag it, they have a look. Well, no, there's an example of a figure that has equal diagonals from the construction, but is clearly not what we mean by it. So this is necessary information, but not sufficient. And I think students need to get engaged in things like that. And of course, there are many others. I'm not going to go through all of that examples. Of course, the next step would be to finally take them to a proof, and now one would be not using proof in the explanation mode, but proof in terms of systematizing local axiomatization, as Freudenthal would call it. For example, suppose we chose this one, definition of an isosceles is any cyclic quadrilateral with at least one pair of opposite sides parallel, and they can check that construction, it works. Then maybe the first theorem might be as two distinct pairs of adjacent angles equal, and then it's really very easy to prove, theorems from there and so on. And there are other possible systematizations. And I think the advantage of doing it this way is that students will learn that definitions are not unique, and we often choose definitions that are more convenient. For example, if I had the choice, I would not choose this definition. I would choose the one based on line symmetry, because the proofs from there are much simpler. And I think engaging them more in the human aspect of it. Almost done. Construction and measurement. I think much of the materials you will often find is a guided experience of guiding learners through constructing a dynamic square or a dynamic rectangle. I would argue that when learners are really young, and I'm not putting an age to it because or inexperienced, I should rather say, with geometry, it is fine to provide them with ready-made sketches of quadrilaterals or triangles in dynamic geometry, which can assist visualization and seeing special cases. I think people make the mistake that they feel somehow that learners first have to construct things to be able to understand them. I think that's the wrong way around. I think you cannot expect learners to construct a square, a dynamic square, something that will always remain in dynamic geometry, a square, unless they already know the properties, unless they already know the interrelationship between the figures. So they should already be at level 3. So that's the wrong way around. I recall a colleague whose name I won't mention from the UK, who once reported at a PME meeting some years ago that they used Gabri to see if that could assist learners' understanding of squares and so on. And they found to their horror that using Gabri didn't help at all, because all the students failed. They couldn't construct a dynamic square. And I responded by saying, but the task that you asked them was totally inappropriate. It was obvious from your data even that you provided that they were at vanilla level 1. To ask them that question is just silly. There's no chance of success, and to say that Gabri didn't help is not explaining why the teaching experiment failed. It was just a poor didactic teaching learning experience. Of course, at Van Hiele level 2, we can use measure and transform features to analyze and learn the properties, and then once they get to Van Hiele level 3, now, if they know the properties already and one can help them to start constructing dynamic sketches for themselves. For example, here they could now go through constructing a rhombus, one way of constructing it, using all sides equal, or they could start off with perpendicular diagonals, etc. Various ways of constructing a rhombus. But unless they've done that already, I think this is an impossible task. I just want to finish off. What I'm saying is not new. Smith already wrote in 1940 about using paper and pencil, having students make constructions to identify the difference between given conditions and the conclusion. So that if they drew something with opposite sides parallel, then the opposite sides were also equal. That is, I think, important. Maybe to finish off, I think criticism issues that are in existence with the Van Hiele theory is well documented. I think research done by Angel, John Pegg and many others have indicated that the learning process is much more continuous than the discrete way in which the Van Hieles describe it. I'm not going to say more about that. There are other theories, for example, Duval's theory that indicates other possible learning trajectories. And I think the issue about hierarchical versus partition classification of thinking, I think, is something that needs more research attention. And lastly, perhaps I would like to just recommend that people perhaps have a look at this paper, the ICME 13 Geometry Survey, of which I was a co-author, if I can find that quickly. Which is, let me just move to the beginning, which we presented last year at ICME 13. It is on my website at that link, recent research, where we did a survey. I won't say of all research, but of a substantial body of research in the previous 10 years under the chair of Natalie Sinclair, that some of you know, Boosie, myself, Keith Jones, and Kay Owens and many others were there. I think I need to stop there. I think I am out of time. I'd rather leave time for questions. I would just like to show one more sketch there. Obrigado. Thank you.